Today we're building a real-time animated chart in Flutter. Yep, we're building a smooth, dynamic line chart that updates live. Imagine you're tracking stock prices, sensor data, or even your heart rate. You want that data to update smoothly, right before your eyes. That's exactly what we're going to achieve. So let's look at the code. Our main.dart file is pretty standard. We have a simple material app. The home widget is set to the real-time chart widget. This is where our animated chart will live. Now let's jump over to realtimechart.dart, where the core logic resides. This is our real-time chart widget, and it's a stateful widget. Because our chart data and the animation itself will be constantly changing, and a stateful widget is perfect for managing that dynamic state. Inside its state class, real-time chart state, you'll notice a few key players. We have a data points list, which is essentially an array that will hold all the values our chart needs to draw. Think of it as the history of our data. We've also got a random object, aptly named random, which we'll use to simulate incoming data. Because in a real-time scenario, data is always a bit unpredictable, isn't it? Next up, a timer. This timer is crucial. It's what triggers the regular updates to our chart, making it real-time. Every second, it's going to tell our app, hey, new data just arrived. And for that smooth, buttery animation, we have an animation controller named Controller and an animation called Animation. The controller manages the animation's progress, like a director setting the pace of a scene, and our animation uses a curved animation with curves.ease in out to give us that natural, gentle start and end to each data point's transition. Finally, you see previous point and current point. These are super important for our animation. When a new data point comes in, we want to animate from where the line was to where it is now. So previous point holds the value before the update, and current point holds the new target value. When our real-time chart first appears on the screen, its initState method runs. Here, we initialize our controller and animation. Notice the vsync argument for the controller. That ties our animation to the widget's lifecycle, which makes it more efficient. Then we set up our timer. This is a timer.periodic timer, meaning it fires at regular intervals. In our case, it's every 1,000 milliseconds or 1 second. And it calls addDataPoint. Let's look at addDataPoint. This is where our simulated data comes in. Inside setState, because we're changing the widget state, we update our previous point to be whatever current point was. Then, current point gets a new random value. We're essentially taking the last value, adding a random up or down fluctuation, and then using clamp to make sure it stays within a reasonable range, say between 10 and 200. This keeps our chart from going wildly off-screen. After calculating the new current point, we do two critical things for the animation: controller.reset and controller.forward. Resetting brings the animation back to the beginning, and then forward starts it playing again. This creates that continuous, flowing movement as new data arrives. Then we have dispose method. It is important to cancel the timer and dispose of the controller. This prevents memory leaks once our widget is no longer visible. Now let's look at the build method. This is what actually creates our widget tree. We've got a scaffold with a clean white background. In the center, we have a container. This container is styled to give our chart that sleek, modern look. It has a specific height, takes up the full width, and has a margin around it. Importantly, it has a box decoration with a slightly transparent blue-gray background, nice rounded corners, and a subtle blue-gray border. This creates a clear visual boundary for our chart. Inside this well-styled container, you'll find the magic of the animated builder. This widget is fantastic for performance. Instead of rebuilding our entire widget tree every time an animation frame changes, Animated Builder only rebuilds the part of the UI that depends on the animation. In our case, that's just our CustomPaint widget. Here's the clever part within the Animated Builder's builder function. We calculate interpolated point. This is the smooth transition between previous point and current point, driven by the animation.value. As the animation progresses from 0 to 1, this interpolated point moves smoothly from the previous point to the current point. We then add this interpolated point to our data points list. We also have a check to keep our data points list from growing indefinitely. If it gets too long, we remove the oldest point from the beginning. Finally, we hand off this list of data points to our CustomPaint widget, which uses a line chart painter to draw the actual chart line. The line chart painter is where the visual rendering happens. It extends CustomPainter, which gives us direct access to the canvas, basically a blank drawing board and the size of our painting area. Inside its paint method, we set up two paint objects: line paint for our actual data line, making it a bold blue-gray shade 704 pixels thick, and grid paint for our subtle grid lines, a lighter blue-gray shade 200 and very thin. Before we draw the main data line, we draw the grid. This is where we create that compelling open-ended feel, as if the grid extends endlessly beyond the container. We define internal horizontal grid lines and internal vertical grid lines. These constants determine how many dotted lines will appear inside our visible chart boundaries. How do we space them evenly inside? For horizontal lines, we calculate horizontal step by taking the size.height and dividing it by internal horizontal grid lines plus 1. Why plus 1? Because if you want, for example, 5 lines inside a space, you're essentially dividing that space into 6 equal segments. Each line then sits at I into horizontal step. So I goes from 1 up to internal horizontal grid lines. This ensures the first line isn't at y equals 0, the bottom edge, and the last isn't at y equals size.height, the top edge, giving us that floating, infinite look. The same logic applies to vertical step and drawing our vertical grid lines, just operating on size.width and x coordinates. We also have a few checks if size.height is greater than 0 for the horizontal lines, if size.width is greater than 0 for the vertical lines, and the number of lines is greater than 0. Just a good practice to prevent any potential division by 0 errors if the widget somehow renders with 0 width. But wait, we're not using canvas.drawLine for our grid. We're calling drawDottedLine. This is our custom helper function, specifically designed to draw segmented or dotted lines. Let's peek inside drawDottedLine. It takes the canvas start point P1, the end point P2, our grid paint brush, and then dash and gap values. These control how long each solid segment is and how much space is between them. The magic here happens with a path object. Instead of drawing one continuous line, we're building a path out of many tiny lines. We figure out the total length of the line we want to draw from P1 to P2. We also get the angle of this line. This angle is crucial because it allows us to move along the exact direction of the line using trigonometry, cosine for x movement, sine for y movement. We then enter a while loop, as long as our current length doesn't exceed the total length. Inside the loop, we use path.moveTo to move to the start of the next dash. We then increment current length by our dash length, and check if current length exceeds the total length. Path.line to draw that dash. Finally, we increment current length again, this time by our gap length. This effectively skips a bit of space, creating the dot effect. Once the loop finishes, all those little dash segments are collected within the path object. Then canvas.drawPath draws all of them onto our canvas in one go. This is how we create those beautiful, consistent dotted lines for our grid. Next, we establish our drawing scale. We have max value and min value set to 220 and 0 respectively, defining the vertical scale of our chart. Our simulated data, as you remember, is clamped between 10 and 200. So by setting max value to 220 and min value to 0, we're telling our chart, look, any data point will fit comfortably within this vertical range. Range then simply gives us the total height of that data scale. 220 minus 0 is equal to 220. This range is vital for scaling our data points proportionally. Don't get confused with min value 0, which might seem redundant since our data is clamped at 10. It's absolutely crucial for real-world scenarios where your data might genuinely start from a different positive value, or even extend into negative territory, ensuring your chart can perfectly adapt to any data range you throw at it. Now, dx. This variable determines the horizontal spacing of each data point on our chart. Imagine our chart area has a certain size.width. We want to distribute our points, our list of data values, evenly across this width. The points.length minus one part in the denominator? That's because if you have, say, 10 data points, you actually have 9 segments between them. So, to space 10 points out, you divide the total width by the number of segments. The ternary operator says, if points.length is greater than 1, meaning we have at least 2 points to draw a line segment, then use points.length minus 1. Otherwise, if we have 0 or 1 point, just divide by 1. This prevents a division by 0 error if our points list happens to be empty or only contains a single point. So, dx is essentially the pixel width allocated to each step between 2 consecutive data points. Then we use a path object because our data line is a series of connected points, not just a straight line. We always check if points.is is not empty, to make sure we actually have data to draw. It's like checking if you have paint before touching the canvas. Then for our very first data point, first x is set to 0. This simply means our chart line starts at the far left edge of our drawing area. First y. This is the crucial vertical coordinate calculation for our first data value, data point at index 0. Let's re-emphasize this. Data point value minus min value. We shift our first data value so that it's relative to our min value. If min value is 0, this just gives us the value itself. Again, min value makes more sense when you have a different range. Try creating charts with different ranges. Range. We divide by the range to normalize this shifted value to a proportion between 0 and 1. So, if the first data point is 110, 110 minus 0, divide by 220 gives us 0.5, meaning it's halfway up our data range. Size.height. We then scale that proportion to the actual pixel height of our chart area. If our chart size.height is 300, 0.5 into 300 gives us 150. Finally, and this is key, we subtract this scaled value from the total size.height. Remember, in Flutter's coordinate system, y equals 0 is at the top and y values increase downwards. To make higher data values appear higher on our chart, we subtract from the total height. So, if the scaled value was 150, meaning 150 pixels from the bottom, 300 minus 150 gives us a first y of 150. This correctly places a value halfway up the data range, halfway down the screen. Once first x and first y are calculated, path.move to tells our path object. Start drawing the line here. Lift your pen and move to these coordinates. No line is drawn yet, it's just setting the starting point. After setting the starting point, our artist then loops through all the points in our data points list. For each I, which is the index of the point, x equals I into dx. This calculates the horizontal x pixel coordinate. Since I starts at 0, the first point will be at 0 into dx equals 0. The second point will be at 1 into dx, the third at 2 into dx, and so on. This neatly spaces out our points horizontally across the chart. This is the same y pixel coordinate calculation we just explained for first y, but now it's applied to each point in our points list. Path.line2. This is where the actual drawing instruction happens for the path. For every point after the initial move to, line2 tells the path to draw a continuous line segment from the previous point to the current point. These new x, y coordinates. This continuously connects all your data points. Finally, once the for loop has finished, our path object now contains all the instructions to draw every segment of our data line, connecting all the points. Canvas.drawPath is the command that tells our canvas to take that entire set of instructions contained in path and draw it onto the screen using the line paint brush properties. And that's our bold blue-gray line. You'll also see should repaint overridden to return true. In this dynamic chart, our data is constantly changing and the animation value is always updating. So we always want the line chart painter to redraw the entire scene to reflect the latest data and animation state. And that's it. Every second, new data comes in, the animation controller plays, the animated builder interpolates the new point, and the line chart painter redraws the smooth line and the cool, open-ended dotted grid. You get a beautiful, flowing, real-time chart. What do you think? Pretty neat how all these pieces come together, isn't it? Alright, here on the screen, you can witness the beautiful real-time chart animating. Notice how the line updates every second, smoothly transitioning between points, thanks to our animation controller. See those elegant dotted grid lines providing a clean backdrop, creating that open-ended, infinite feel we talked about. This isn't just a static graph. It's a living visualization of data, updating right before your eyes, just as it would in a live application.